Alright, so what we want to do today, or at least what I want to do today, which means today, is talk a little bit about some fun things in probability. Unfortunately, one of the other things we have to do today is go through some of the mechanics of joint distributions. So I will try to have, a semi-interesting example to just, go through some of the mathematics and the basics, and then we'll switch into coin tosses, do some experiments, and try to conjecture what the theorem should be. And then we'll try to prove the theorem. And if there's time, I'll talk about generalizations of the theorem and applications to finance, to optimizing your portfolio, minimizing your risk. And if there's really time, which I doubt, I'll talk about differentiating identities, which is one of the most powerful techniques in the subject and one of my favorite ideas in mathematics. How many of you know the Pythagorean formula? Okay. How many of you can prove the Pythagorean formula? I mean, James Garfield, one of the most famous Williams alums, does have credited to his name an original proof of Pythagoras. Pythagoras, it's a beautiful formula, but it's not as useful as the geometric series formula. I can generate infinitely many new equalities from the geometric series formula. I can't generate infinitely many equalities from the Pythagorean formula. So I'm going to show you a technique to create new identities from old. And when you think of how much work it takes to create an identity, to prove an identity in mathematics, if you all of a sudden have a technique that can give you more, that's quite useful. Okay, so let's start off with just some of the basics. So joint density. For the most part of the class, we look at just single densities. We have a function of just one. We just have one output that's coming out. I'm tossing the coins and I'm looking at how many heads do I have. But you could have a value that depends on several things. For instance, if I'm thinking of temperature, temperature could be a function of latitude and longitude. Okay? Typically, you will have things that will vary on many different parameters. What's the main difference, do you think, in calculating probabilities from a joint density versus something that just depends on one variable? What are you going to have to use? Double integrals, triple integrals. So you're going to basically have to use more multivariable calculus. You are all masters at multivariable calculus because you're in this class and you've satisfied the prerequisites, so I will not, for the most part, give you multivariable calculus problems because I know you know how to do them. Okay? And in fact, that's not circular logic. Okay? And in fact, I'm going to show you later this semester how to avoid doing multivariable calculus integrals by cleverly using the theory of normalization constants. It's an incredibly powerful idea that allows you to not have to worry about, for instance, what is the change of variable formula going from Cartesian to spherical coordinates in 2013 dimensional space, which we will need later in the semester. And there are ways to bypass that. All right, so joint densities. We say x1, x2, xn have joint density function f sub x1, xn. If S is in Rn, then the probability that my tuple x1, xn lives in S would just be the integral over that region S of my density function x1, xn, x1, xn, dx1, dxn. Okay? So, in one, if n equals 1, this is just the standard way we calculate probabilities. What's the probability I'm in an interval AB? I just integrate over the integral AB. What's the probability that my tuple takes on a value in some box S, or some more general shape S? Well, I just integrate my function over that region. Okay? How many of you like doing multiple integrals and change of variable formulas? How many of you prefer to do one-dimensional integrals? Okay. What would happen that would allow us to convert this to one-dimensional integrals? What would we need?
The function is separable?
So that the function is separable. I have a function right now that depends on all these. So for example, maybe f of x1, x2 is x squared y to the fourth cosine squared x squared plus y squared times some normalization constant c and 0. And maybe this is, 0 less than equal to x, y, less than equal to 1701, otherwise. Do you think this is a probability density function for an appropriate choice of c? Is this non-negative? Yeah. Does it have a finite integral? Yeah. I can find a choice of c. I don't know if I would want to find that choice of c. It's not as horrible as it looks. I at least have x squared plus y squared. Maybe I can shift two polar coordinates, but unfortunately I'm integrating over a rectangular region. So this would probably not be pleasant to find the value of c exactly. But there would be a value of c. This would not be fun. A better example would be f of x1, x2, and this should be xy, I guess, equals x squared y to the fourth cosine squared x squared times cosine squared y squared times c in the same regions as before. Now if I wanted to integrate this, it's much better. Because now the integral splits and I'll have my x integral and I'll have my y integral. Okay? So the goal is, if possible, work with independent random variables and then they split. And so the key result is x1, x2, xn are independent if and only if. Has everybody seen if? So IFF means if and only if. Very good convenient notation. If the joint density function fx1, x2, xn of x1, xn is f x1, x1. How many of you are having fun writing all this? x2, x2, f xn, xn. There's a faster way to write this stuff on the right-hand side. This is just a product, k goes from 1 to n, f of xk, xk. And as you're working with many variables, you can see why the product notation is so convenient. It's not fun to keep writing all of this stuff down. Okay? I do think sometimes it's a little bit easier visually to see something like this than to just write things in product notation, but in the interest of space. Okay? So this is a really nice result. So related to this is the notion of a marginal density. So you basically integrate out all but one variable. So what value of n has the easiest marginals to calculate? So for what value of n do you think it's very easy to calculate the marginals?
0, 1.
No. Which?
1.
1, right? If n equals 1, the marginal density is the same as the density. What I'm basically saying with the marginal density is, let's say I'm looking at my temperatures on the surface of the Earth. And what I could be saying is, I don't care about the latitude. I just want, in some sense, integrate out all of that stuff and just give me what's going on for this whole latitude over here. Certain marginals will be easier to calculate than others. If my joint density function splits, it's very easy to integrate out the other stuff. What will the other stuff integrate out to? 1. The marginal density has to be density itself. So we know the integral over the whole region r to the n of f of x1, xn, x1, xn, dx1, dxn, that has to equal 1. So imagine now we integrate everything out but the ith component. So we can let fxi of xi is the integral x1, xn go from 0 minus infinity to infinity, but no xi here. F of x1 dot xn, x1, xn, dx1, dxn. So is this a probability density? Well, it's going to be non-negative because my density here is non-negative. When I integrate something that's non-negative, I can't get something that's negative. So this will clearly be non-negative. Does it integrate to 1? Yes, if I integrated every variable from minus infinity to infinity, I would get 1. So if I want to see if this integrates to 1, I have to integrate this from minus infinity to infinity. That's the missing integral I need. Okay? When you have lots of integrals like this, what do you have to be careful about?
Order of integration.
Order of integration. Technically, this is integrating maybe first x1, then x2, then x3, then xn. Does it matter which order I integrate? If I write it like this now, and then I integrate over xi, I've switched the orders of integration. If you want, I will send you a video from Cameron about how to interchange orders of integration. This is from when he was 2 years old. It's not that hard to learn how to interchange orders. But you have to be careful. You can't always switch orders. Now, fortunately for us, we can always switch orders for problems like this. And the reason we can always switch is what we have here is non-negative. So there's no danger switching orders of integration. So how many of you have heard of the Fubini theorem or Fubini-Tonelli? This is something you should have seen in Calc 3 when you can switch orders of integration. If the integral of the absolute value is finite, then you can switch. Okay? So I'm going to give you an example where you can't switch orders of integration. Yes?
So why is the integral still 1 when you pull out the x of I?
So if I integrate over all of Rn, I get 1. So what I'm doing here is I'm integrating over r to the n minus 1. There's one variable that I haven't integrated over. So when I integrate over that variable now, I've now integrated over everything. And I know from up here that the integral over everything is 1.
Right.
So then that means if I just integrate this over xi, it has to integrate to 1. So the marginal density is basically telling you what's the probability the ith variable takes on this value when I don't care about the values of everything else. Alright, my geography is terrible. Is it latitude that goes north and south?
Yes.
Okay, so the equator is 0?
Latitude.
Yeah.
0 latitude,
Like
okay.
runs of a ladder.
Ones of the ladder, okay. So, do you think your temperature depends on your latitude?
Yes.
Yes, right? And so if I give you some information about your latitude, especially if I tell you at the North Pole or the South Pole, you'll have some really good information about what the temperature is like. Do you think temperature depends on longitude?
Yeah.
Well, I mean, theoretically, like areas at different longitudes will have
If you go
different
along,
temperatures.
if you go along the longitude with us, you end up in like the Sahara, or you end up in like
So
southern
well,
Italy.
Depending on the latitude.
Right, so these things are definitely related to each other. Different parts of the Earth, even if they're at the same longitude, will have very different temperatures. They'll be very different regions. And so what I'm doing here is imagining, I want to know essentially what's the probability of a certain temperature at a certain latitude, integrate out of all possible longitudes. And so I want to go all the way around the circle. And that will give me some kind of probability distribution of observing a certain thing. What if I told you your longitude and your latitude? Yes, you know where you are, right? And so this is basically giving you less information. It's not surprising that you have less information, because I've only specified, I've integrated out one thing. Alright. How many of you have seen an example where you can't interchange orders of summation? Or orders of integration? Alright, let me give you my favorite example. I'm going to do it with two sums rather than two integrals. If you want, smear things out a little bit. Okay? And then you can make it confusing. So what I'm going to do, in the interest of time I'll only draw a few of them, is I'm going to look at all of the points that have non-negative integer entries. Alright, so as you probably realize, there's a lot of such points. And I will stop. So cannot always switch sums. You must be this tall to teach 341. Okay, so here is 0, 0, 1, 0, 2, 0, and so on. This is the point 0, 1, 1, 1, 2, 1, and so on. This is the point 0, 2, 1, 2, 2, 2, and so on. Okay? And I'm going to give you a sum of numbers a, m, n. And in one, I'll have n go from 0 to infinity first, and then m go from 0 to infinity. And in the other, in a surprising move, I will have m go from 0 to infinity, and then n go from 0 to infinity. Alright, I'm going to define my terms a, m, n as follows. Plus 1, minus 1, 0, 0, 0. 0, plus 1, minus 1, 0, 0. 0, 0, plus 1, minus 1, 0. 0, 0, 0, plus 1, minus 1, 0 forever. Okay? Let's do this one first. So what I'm doing is I'm fixing n, and I'm letting m vary. Okay, so this is the, so if I fixed n, I am always at a certain height. So what can you tell me about the sum of a, m, n as I go through a row?
It's 1 at the first one.
It's 1 in the first one and everything else is 0. So what do I get for this side?
1.
1. Now here I fix a column. What is the sum in each column?
0.
Okay. So here's an example where you can't switch the order of summation. And the problem is that the sum of a, m, n in absolute value is plus infinity. Whenever there are infinities in mathematics, you should be careful. Okay? And so the issue over here is I can't switch. When I try to break things up and do things rigorously, there could be too much in it. There's a lot of cancellation going on. If you've taken real analysis and you know the rearrangement there, this is another fun example of what can go wrong. Okay, let's do an example of joint densities now. And so, let's take the example of we'll toss a fair coin 5 times, and I will assume the tosses are independent. So, toss fair coin 5 times, toss is independent. X will be the number of heads in first 3 tosses, Y, number of heads in the last 2. And so, what I can do is I can make a table and record the values. So here's X, here's Y. So what are the possible values for X? 0, 1, 2, or 3. The possible values for Y are 0, 1, and 2. Okay. So we have to go through and calculate all the probabilities. So I have to look at what's the probability that X equals 2 and Y equals 1. So what would be the probability that X equals 2 and Y equals 1? So tell me how you would calculate it, not necessarily what the answer is. So how are you getting 1/8?
Probability of 2 heads in the first one. Probability of 1 head in the second.
Okay, what's the probability of 2 heads in the first 3 tosses?
Is it 1/2 times 1 head times 1?
Well, so if you do that, you do a specific sequence of 2 heads. How many different ways can I get 2 heads? In 3 tosses. 3 choose 2, right? 3 choose 2. I have 3 tosses, 2 of them can be heads. What's the probability of each sequence? Well, since it's a fair coin, so x equals 2, y equals 1. X equals 2, I get 3 choose 2, 1/2 squared times 1/2. And if you really want to be overly pedantic and waste chalk, the second 1/2 is 1 minus 1/2 to the 3 minus 1.
3 minus 2.
3 minus 2. Okay, if you want to be pedantic and correct, it's 3 minus 2. If you just want to be pedantic and incorrect, you can do 3 minus 1. Okay? So, really, no one is going to write 1 minus 1/2 to the 3 minus 2. You're going to just write 1/2. This is one of the advantages of a fair coin. All sequences are equally likely. So I just need to know what the count is. What about the probability that y equals 1? So I want 1 head and 2 tosses. I want exactly 1 head, actually, and 2 tosses.
2 choose 1
So it'll be 2 choose 1
times half.
times 1/2 to the first, 1/2 to the first. So how would I now calculate the probability that x equals 2 and y equals 1? So can I just multiply those probabilities? So they're independent, right? The probability that x equals 2 and y equals 1 is the probability that x equals 2 times the probability y equals 1 because they're independent. So here, this number here is just going to be 3 times 2 is 6. And then, how many powers of 2 do I have? I should have 5. So that's just 6 to the 30 over 32. 1 down, many to go. Right? So, let's go through this entire row. We already know the probability of 2 heads is just 3 over 8. So what's the probability that we have? Oh, I think I have drew an extra. Sorry. What's the probability? Oh, see, it's not so bad. Look at how much of the table we've already taken care of. All right. So what's the probability that I have 0 heads and 2 tosses? That's just 1/4. So this is going to now be 3 over 32. What's the probability I have 2 heads and 2 tosses?
3 over 32.
I'm sorry? 2 heads and 2 tosses.
Well, it's the same probability I have.
1/4.
It's just 1/4 again. So it'll be 1/4 times 3/8 is 332. Okay. Now let's do, what's the probability I have 3 heads and 3 tosses? 1/8. And so 1/8, and we had this was 1/4, so this should be 1 over 32. This will also be 1 over 32. And then the probability of having just 1 head and 2 tosses was 2/4. Right? So we'll get 2 32nds, I believe. Why am I writing this 2 32nds and not 2 16ths? Yes, I can sum them much easier later. All right, now let's do the probability that x has just 1 head. What's that going to be? So that x is, yeah, it's just 3/8 again. So this will be 3/8 times 1/4 is 3 32nds. 3 32nds, and then here it's going to be 1/2. So it'll be 6 32nds. The probability that x has no heads is just 1/8. So this should be 1 32nd, 1 32nd, and then 2 32nds. So if we haven't made any mistakes, what should all these numbers add up to? 1. 2, 3, 4, 10, 16, 22, 25, 28, 29, 30, 31, 32. All right. Maybe it's not the most efficient way to count, but okay, it adds up to 1. There. So now, since we had so much fun counting, let's count some more. let's extend the table a little bit. I'll draw a thick line over here and a thick line here. Let's count just this row. So if I count this row, I get 2, 3, 4, 4 out of 32. And 4 out of 32 is the same as root 8. If I count this row, I get 12 out of 32. 12 out of 32 is the same as 3/8. Thank you. Okay.
Isn't that the probability of doing one?
Yes. If I count just this row, this is what's technically known as an aha moment.
3/8.
Yes. Now, are you saying 3/8 because you know that's what the answer is, or you're actually counting?
Well, we just did the same math. But I'm not going for it.
And this one, well, we've already done that math. Now over here, if we count this way, we have 8 out of 32, which is 4. And I like the idea of using the same math. We have the same thing over here. We have 1/4. And now if we come straight down here, oh, that's a lot of stuff. 2/4. Is it 1/2 or is it 2/4?
1/2.
It's 2/4. Make algebra nice. Okay? And now notice this as what's going on here. The 8 reminds us of what we would get if we tossed a fair coin 3 times. Or tossed 3 fair coins. And so if you look at this, this is the probability that x equals 0 and y equals 0, x equals 0 and y equals 1, x equals 0 and y equals 2. By adding all of these 3 things, I'm basically saying I don't care about the value of y at all. I just care about the value of x. So I'm adding all this stuff together. This is the marginal of x. Of being 0, this is the marginal of x being 1, x being 2, x being 3. What happens if we go down? We're getting the stuff for y. And I'm saying I don't care about the value of x, I just care about how often is y 0. Y is 0 1/4 of the time. And then if you take these and add, what would you get? No, you'd get 2. I said if you take these and these, you get 2. You don't add those. Right? If I take these 3 numbers down here, they add to 1.
The corner would be
Well, it depends what you're adding. If I just add all the stuff up here, yes, the corner would be 1. But if I add this and this, I get 2. Now if I just add this way, I get 1. If I just add this way, I get 1. You want to make sure you don't double count. And so if you look at it, once you've done this, you've already counted everything once and only once. Once you've done this, you've counted everything once and only once. So if you just do addition from this way or just from this way, you can put in a 1 here. And that basically just says it is a probability, it adds up to 1. Years ago, I won't say that this was a friend of a colleague in marketing because it would be wrong to say the field's name, but they couldn't understand why it was wrong that the probability should add up to 2. And they were essentially doing something like this. And one of my colleagues was trying to explain to them, no, you can't add everything and then add everything again. Okay, so let's do another example of joint densities. And so since it took so long to make that table, I'm going to just write down some values. So I'll use the letters U and V, 0, 1, 2, 3, 0, 1, 2. Okay, and so the values are 1/16, 2/16, 1/16, 0/16, 1/16, 3/16, 3/16, 1/16. My handwriting's really messy. 0/16, 2/16, 2/16, and 1/16. Okay. Probability or not probability? So I get that this is adding up to 17.
Yeah.
So this is not a probability. And so, what does this mean?
Copy.
I'm sorry, I copied it wrong.
Should in the 2/16 in the row of 1, shouldn't that be a 1? By symmetry with everything else.
This one?
Nope, up 1.
This one?
That would be a 1.
Let's see. I like this one over here. These numbers I like. 2, 6, 7, 8. I like these numbers over here. So the mistake is definitely in one of the ones over here.
1, 2, 1, and then
Everything's sort of like just symmetrical in a way.
So
is the marginal?
this one I like. This one I
Yeah,
like.
I see.
So it's one of these two that I don't like. Oh yeah, this is the one I don't like, yes. Now I'm in trouble. Good call. So I wrote down the wrong ones, but I forgot to write down what the correct one was. So it's very easy to check and see if it sums to 1. Is there anything else we have to check to see if it's probability?
All values are non-negative.
All values are non-negative. All values non-negative. Yes. So this is a joint density function. What's it coming from? Yes.
A suspicious hunch tells
A
me
suspicious hunch.
if coin 1 and coin 4 were glued together,
Ah.
this would be the density function. But that's just a hunch.
That's just a hunch. An outstanding hunch.
Or if they score the same one.
So, glued coins 1 and 4, the rest are independent.
Now, did I glue them so that they are always the same or opposite?
I think it's that they're always the same.
So how can you tell quickly that there must be some kind of dependence? Yes.
Well, there's no when they weren't glued together. You could get 3 heads and 0 heads for the second half.
Mm-hmm.
But now if you get a head with
Well, that's just comparing that to this.
okay.
So what you're saying is this can't be the same as this. I agree. They're different.
Yeah.
They have different probabilities. It's not the same process. But maybe it's a different independent process.
Well, if you look at the marginal of a column with a 0 in it,
Okay.
if you, it's like the bottom row, for example.
Okay, so the margin here, let's write down the marginals. That's a good thing to have. It should be 1/4 here, 1/4 here, and 1/2 here. Call it 2/4. Alright, so there's the marginals down there. And let's write the marginals over here. So the marginal here would be 1/8, 3/4, 6/8, I'm sorry, 3/8, 3/8, and 1/8. So I've got my marginals now. Okay, now what?
Well, if you were doing the same thing as before and were independent, you would be multiplying the two probabilities.
Excellent,
You can't
excellent.
get 0 out of 16 by
Excellent.
multiplying any of those.
Excellent. So to be independent, the probability that I take on the value xy is the probability that x equals x times the probability that y equals y. So I can use the marginals. And so here I've got the marginals. Notice these have the same marginals. So we've just proved a nice fact. Just because two systems have the same marginals does not mean that they're the same. There's information that's lost. And so here, this is supposed to be the product of the marginal that x equals 3 times the marginal that y equals 0. The probability that y equals 0 is
Or 1/4.
1/4. The probability that x equals 3. So 1/8 times 1/4 is not 0/16. So as 1/8 times 1/4 does not equal 0/16, not independent. So here, the probability that x equals x and y equals y is the probability that x equals x times the probability y equals y if independent. And it kind of makes sense. If they're independent, knowledge of one doesn't give you any information about knowledge of the other. And so then if I know the marginals, well then I know the distribution of x, I know the distribution of y, I should be able to figure out the joint distribution. The joint distribution is just the product of the two distributions. If, however, there are dependencies, then it's not enough to know the marginals. That's not surprising. You know, the marginals washes away the dependencies. Okay. So I really like this example as it highlights the fact that the marginals is not enough information. Think of it as I have this table, and I'm basically telling you certain slices this way and certain slices this way, and then I want to deduce everything inside. And the question is, when can I do that? I need a lot more information. There's a lot of ways to fill things in. Okay. Any other questions on this before we move on to expectation, or return to expectations? We've been to expectation before. Okay. So what I want to do is not just write down the formula for the answer. I want to try to experimentally figure out what we should conjecture. And so here's the problem. We have n fair coins. What is the expected number of heads in an n tosses? Is this enough information to solve the problem? Okay, what else do you need?
Never mind.
Okay. So what else do we need to make this a well-posed problem? Yeah, we need to know if they're independent. Maybe I have the coins all glued together into the giant super coin. And I'll just toss the whole super coin, and they'll all either land heads up or they'll all land heads down. Maybe I have some kind of interesting pattern where I'm alternating heads, tails of the coins as they're glued together. Or maybe I've even got just the coins in the prime indices being heads. Right? I need some more information. Let's assume independent. So what's the probability that x equals k? So what's the probability that we have k heads in n tosses? Yes?
N choose k 1/2 to the k, and 1 minus 1/2 to the n minus k.
Okay. So going for the pedantic metal, and we can simplify that. Okay? So now, the mean, mu of x, is the expected value of x, is the sum, k goes from 0 to n, of k times n choose k, 1 over 2 to the n. There's lots of different ways to write the algebra. One thing that's particularly nice here is that I have the 1 over 2 to the n, and I can just pull that out. And I'm left with trying to understand a sum of a polynomial in k times a binomial coefficient in k. Or, I could do the pedantic version. K goes from 0 to n, k, n choose k, 1/2 to the k, 1 minus 1/2 to the n minus k. Which way do you think is easier to analyze the sum? Pedantic or non-pedantic? Nope. So correct your answer.
Pedantic.
Yes. There's an advantage of writing it this way. What I'm going to do is I'm going to eventually give myself a parameter to vary. Now you might think, why am I going to vary a parameter? It's a fair coin. Okay? The advantage of allowing myself to have a parameter that varies is I can now use the tools of calculus. Everyone here should have spent at least 1.5 years of their life, if not more, learning calculus. Right? There is a reason for this. Okay? We want to be able to use those tools. And it's going to be very useful to consider the more general problem of the sum k goes from 0 to n of k, n choose k, p to the k, q to the n minus k. And then at the end of the day, what will we take q to be?
1 minus p.
1 minus p. But it's actually better to keep q as a free variable as well for a while. Okay. So let's try to conjecture what the answer should be. What's the simplest value of n that I will let you get away with? 1. Alright, so if n equals 1, the expected value of x would be what? So we'll be summing k goes from 0 to 1 of k, and I'm sorry, it's just now 1 choose k times 1 over 2 to the first. What do we get? So we'll get 0 plus 1/2, which is just 1/2. Right? I only have two possibilities. Building on our success, when n equals 2, we want the expected value of x. It's a little bit more now. It's now the sum, k goes from 0 to 2, of k times 2 choose k times 1/2 squared. Do I have to bother writing what I get when k equals 0? Does k equals 0 contribute to the mean? No. I'll still write 0 because I'm pedantic. 1 times 2 choose 1 is times 1/2 plus, now when k is 2, 2 choose 2, 1 times 1/2, I'm sorry, times 1 over 2 squared. So this should be 2 squared. And what does this equal? So I've got a fourth, 2 plus 2 is 4, this equals 1. We'll do one more. Expected value of x, we have the sum, k goes from 0 to 3 of k, 3 choose k, 1 over 2 cubed. Now in business they often say your 1 point determines a line. Your 1 data point is more than enough for marketing. If you want to try to get some sense, take a few more points. Okay? And this is actually a good chance to give you some advice. This came up recently. I will be giving this advice to my complex analysis class. Please file this under the blatantly obvious. 2 years ago, a colleague of mine set up a job interview for one of her students in New York City. The company contacted her and said, "We're very interested. We'd like to meet you at 8:30 at the following place." She wrote back, "I'm not a morning person. Let's meet in the afternoon." You can probably figure out what happened. It also made it much harder for my friend to recommend students in the future. Okay? So, business, in addition to 1 point determines a line, if they tell you we're meeting you at a certain time, that's the time you meet. And you say, "Thank you, I will be there." Over here, 0 plus 1 choose, 3 choose 1 is? 3. Times 1/8 plus k is now 2 times 3 choose 2. 3. And 3 choose 3. 1. But k is 3 times 1 times 1. So I have, let's see, I have 3 plus 6 is 9, plus 3 is 12. 12 over 8 is also known as 3/2. And I'm going to write 3/2
Could you write it as,
in the old fractional way. I'm sorry?
could you write it as a number too?
So we have a conjecture,
Just
right?
So many
If
thoughts.
n independent, I'm sorry?
I'm just seeing so many thoughts coming out of this class, so many hunches.
Hunches of Williamstown. Okay. If n independent tosses, the expected value of x is equal to n/2.
or that n times p.
Even better. Well, generally, expected value of x equals np.
But we
Well,
should
given
change
what we
that
know
equals
so far.
2 over 2.
What?
working from where P is 1/2 and Q is 1/2.
Right.
So N over 2 is NP, but it's also NQ.
Ah.
That's just a coincidence. That's not generalizable. Oh, there we go.
I like this. Will we be able to figure out which one of these is right by doing larger values of n like this?
In this example, no, because
No.
P and 1 minus P is.
Right. Can you quickly disprove that it can't be n times 1 minus p? It's an outstanding comment. Please email me that it could be n times 1 minus p. That's consistent. But you can disprove that it can't be n times 1 minus p.
Let P equal 1.
Let p equal 1. Right? How many of you have ever had the Mobius coin? The Mobius coin. The Mobius coin is the parabolist's dream. It always lands on heads. Okay? It's the one-sided coin, okay?
Have you never seen that?
Oh, yes, I'm saying, okay.
Okay.
Yes.
Harvey
But I'm saying he doesn't,
The
but
jump from Batman to the Harvey Dent is a little far.
is this your darkest classic? No. But he doesn't have a one-sided coin.
He has a double head coin until he gets murdered.
Wait, does this coin have heads on both sides?
Yes.
Oh, so it's not really independent, it's not really random when he tosses it. He always
Once
No.
in until he.
Before he got his
Okay.
face burned.
Alright.
Yeah, after the phase burn.
Okay. I'll have to review that. So if we toss the Mobius coin, then if we toss it just once, we always get a hit. And toss it twice, we always get a hit. So this is eliminated by the Mobius coin. So what I like is we now have a conjecture. And the question is, how can we try to prove this conjecture? So when you see something like this, where you know if n equals 1, n equals 2, n equals 3, what would you like to try to do? Yes?
Use induction.
So one thing is to try to use induction. It's the most natural thing to try here. The problem is the induction is going to be painful. Because what I'm going to have to do is I'm going to have to change n to n plus 1, so these sums are going to change. Okay? No, okay, so we have some changing sums, but we actually have a formula for n plus 1 choose k. What could we use for that formula? So do you know any formula for n plus 1 choose k? I feel so too. I think I even gave a proof by story with with a visiting student from Amherst.
Oh.
Right? So we need to study the sum, it goes from 0 to n, of k, n choose k, 1 over 2 to the n. N plus 1 choose k plus 1 is n choose k plus n choose k plus 1. So if you want to prove it by induction, use this. You may need to write k as k plus 1 minus 1. You may need to use the sum of like n choose j. J goes from 0 to n equals, with a 1 over 2 to the n equals 1. So if you use, I think, all of these ingredients, and of course you add algebra, and then add more algebra, then you simplify, and you add some more algebra. If you do all that, you will get to the right answer. So for extra credit, make this work. Prove this using Pascal's triangle. There's other ways to prove this. Can someone give me another approach to try to prove this?
Well, if they're independent, you're doing something with probability p n times.
So that's what we're going to lead into on Wednesday. Is the notion that the sum, the expected value of the sum is the sum of the expected values, and break this up into n different processes. And then the other way we're going to do it is differentiating identities, which is my favorite way of doing this. Okay, so if you haven't signed up for the Putnam